Take a look at this collapsing mountain of refuse. We generate an astounding volume of daily waste globally, but almost all of it is funneled into incredibly constrained physical spaces to be sorted out. Inside a typical sorting plant, the sensory environment is overwhelming. The air is thick with pervasive dust, and the constant mechanical roar of hoppers and rapidly moving conveyor belts makes it a deeply challenging place to work. This diagram illustrates the sheer weight of that expectation. On one side, you have a massive 280,000 tons of mixed recycling generated every year. On the other, the entire burden of sorting it falls onto a single human team of just 24 agency workers. And what comes down those belts is highly unpredictable. In a single minute, a worker might have to grab a tangle of old VHS cassettes, immediately followed by jagged, heavy blocks of concrete. The sheer volume of material moving through these plants is only manageable because the heaviest physical sorting is still handled by a workforce that is pushed to the limit of human endurance. But relying on pure endurance to process our trash exacts a severe physical toll on the people standing on the line. You can see the consequences in the safety data. This chart tracks workplace hazards, showing the injury rate in the waste sector spikes 45% higher than the national average. When factoring in these hazards, retention plummets. Keeping workers is incredibly difficult, driving an unsustainable 40% annual staff turnover. The economic math of waste management is failing. The system is nearing a breaking point because human physiology simply cannot endure the baseline requirements of the job. To stop the constant cycle of turnover, facility operators are inserting technological interventions directly onto the sorting line. Enter Alpha. It's a humanoid robot engineered specifically to occupy the exact physical footprint of a human picker. The economic logic here is entirely spatial. As we see in this blueprint layout, building a robot with a humanoid shape allows it to slide seamlessly into a standard workstation. The plant doesn't have to spend millions of dollars redesigning its entire conveyor infrastructure. But physical shape is only half the equation. Here, a human worker wears a VR headset in a system called HoloLab, physically executing successful picking motions to train the robot's data model on exactly how to move. This early strategy of automation relies on perfect digital mimicry. By explicitly replicating human mechanical movement, operators can bridge the immediate labor gap without tearing down the existing facility. Mimicking humans is an effective patch, but other robotic architectures are being deployed that abandon the human form entirely to surpass our physical limits. A sorting system built by a company called AMP completely eliminates traditional mechanical robotic arms from the line. Looking at this top-down vector diagram, you can see their mechanism. They utilize highly precise air jets. As targets pass by, rapid pulses of air flawlessly deflect specific items off the belt and into designated sorting chutes. Removing the weight and inertia of a mechanical arm allows for extreme speed. The airjet system processes items at 8 to 10 times the pace of a manual human worker. Speed solves the volume problem, but extreme unpredictability in the waste stream remains a massive hurdle. That's where companies like Glacier are deploying advanced AI. Glacier's AI models have trained on over 1 billion discrete items. That vast dataset allows the system to recognize and adapt to catastrophic anomalies moving down the belt in real time. In practice, that means spotting active dangers. In real facilities, these systems have accurately identified and navigated around everything from spraying beer cans to live hand grenades mixed in with the household trash. Advanced AI and pneumatic systems permanently remove the bottlenecks of human speed and human vulnerability. This allows facilities to transition to continuous operation, running 24 hours a day, 7 days a week. As the machines accelerate, we have to look at what happens to the manual workforce displaced from the line. This stark visual contrast illustrates behind this technological pivot. We're balancing extreme operational efficiency against the threat of massive human job displacement. Academic researchers studying waste processing argue this is a mandatory evolution. The automation transition maximizes material recovery while actively rescuing human beings from highly dangerous, heavy lifting environments. Facility owners are mapping out a transition strategy for their staff. The plan is to upskill current manual pickers, turning them into the technicians who oversee, maintain, and continue to train the new robot workforce. The robotic integration into the waste industry proves that eliminating hazardous jobs forces a difficult but necessary recalculation. As the physical dangers disappear, we must redefine the true value of human labor in a fully automated economy.